Hello, this is section 2.1 and we're going to look at graphs. Now, at any point during this video, please feel free to pause and catch up or rewind or whichever you need to do. And then if you have any questions, anything that you didn't understand, please don't hesitate to let me know. Okay, so we're going to go ahead and start. Our objectives for this one are graph points on the coordinate plane, identify parent functions, use transformations to graph functions, solve application problems, and graph linear functions using x and y intercepts. Okay, so we're going to look at part one, which is the coordinate plane. So we've got our x-axis, that's our horizontal axis, and then we have our y-axis, that is our vertical axis. Um, we have the origin, which is 0, 0, and we have our quadrants, 1, 2, 3, oopsie, that was misspelled. Quadrants. 1, 2, 3, and 4 here. And then when we give a point like origin 0, 0, we put it inside parentheses with x first and then y. Alphabetical order. Okay, let's look at example 1. So is each point a solution to the given equation? So we're given a point here, which is 3, 4, and now again, it's x first and then y. And then what we're going to do is we're going to plug in the x, where the x is in this equation, and the y, the 4, where y is. So we're rewriting it. 3 minus 2 squared plus 4 plus 2 squared equals 6. So for this point to be a solution, this has to equal. So we're going to go ahead and order of operations, parentheses first, 3 minus 2 is 1 squared, 4 plus 2 is 6 and squared. So now 1 squared is 1, 6 squared is 36. Well, 37 does not equal 6. So this is false, which means that no, the point is not a solution to this given equation. Okay, let's try another one. We have x is 1 and negative 3 is y. So we're going to plug it in. 3 times 1 minus, and then y is negative 3. So remember that we have the minus sign and then we have the negative in front of the 3. So we've got to have both negatives on there. And then minus 6 equals 0. So 3 times 1 is 3. A negative and a negative is a positive. 3 minus 6. Left to right, 3 plus 3 is 6, minus 6. 0 is 0, so that is true. So the point 1, negative 3 is a solution to 3x minus y minus 6 equals 0. Okay, on this next page, we're going to look at some parent functions. Before we do that, we're defining the domain and the range. So the domain is the function input values, and that is always the x values. Range is the function output values, and those are the y values. All right, let's start with a linear function, y equals x. So y equals x looks like this. It's an uphill function that goes through the point 0, 0. So when we're looking at our zeros here, that is where so that's the same thing as the x-intercept. So where does it cross the x-axis or where does it touch the x-axis? Well, in this case, it touches at point 0, 0. Now let's go back and look at the domain. So remember that domain is the x. This keeps going all the way to infinity, and the x's keep going to the left, which is negative infinity. So our domain is from negative infinity to infinity, which is all real numbers. It just keeps going and going. There's nothing, it's not stopping anywhere. Range, the same thing. Um, it keeps going up to infinity, and then it keeps going down to negative infinity. And we always start with the negative first. So negative infinity to infinity. Um, and when we're writing domain and range, or when we're writing negative infinity or infinity as domain or range, we always put it inside parentheses. Now, our last thing to do for the linear function is to look at its end behavior. Well, as we can see, it goes down on the left and it goes up on the right. So that's its end behavior. Next one is the quadratic y equals x squared here. And that one, the graph is called a parabola. It is a U-shaped graph like this, and it goes through the point 0, 0. So again, our 0, the x-intercept is 0, 0. Okay, so now if we look at the domain, it keeps going to the left and the right. So our domain is negative infinity to infinity. Our range, though, it doesn't go um, it, to the negative numbers. It stops at 0, but goes all the way up. So 0 is where the range starts, and we are going to put it in a bracket because 0 is included in it. So it goes through that point. It's on that point 0. But then it goes to infinity, and again, infinity and negative infinity are inside parentheses because it's not a set point that we're it just keeps going and going. End behavior goes left up and right up. Okay, next one is a cubic, y equals x cubed. That one looks something like this. Again, looking at the domain, it goes up and it goes down. That's the range that goes up and down, sorry. So the range goes from negative infinity to infinity. That was the range. Domain is the x. So left and right, it keeps going and going, negative infinity to infinity. So all real numbers for both of those. Now, our 0 x-intercept, it crosses the x-axis at 0, 0. So that is our 0. And end behavior is that it goes down on the left and up on the right. Okay, next one is the absolute value, y equals absolute value of x. And that one is a V shape, like this right here. So our domain, it's still going from negative infinity to infinity. Range, it starts from 0. 0 is included. It keeps going up. So 0 to infinity. Our 0, where it crosses or it touches the axis, is 0, 0. And in behavior, it goes up on the left and up on the right. Okay, next one is our square root. And our square root looks something like this. Now, again, it starts from 0, 0, so that's our 0. Now, if we look at this, the domain starts from the y-axis and goes to infinity. So our domain is 0 to infinity. Again, the 0 is in a bracket. and infinity is in parentheses. Same thing for the range. It starts from 0 and goes up to infinity. End behavior is going up to the right only. Okay, last one is the cube root. Y equals the cube root of x. And that one looks something like this. There we go. Again, if we look at the domain, it keeps going to the left and the right. So it is negative infinity to infinity. Range goes up and down. So negative infinity to infinity. And our 0 is 0, 0. Again, it goes through that origin. Our end behavior is down on the left and up on the right. Okay, so next thing, so these are actually before we go on to the next page. So these parent functions, your life will be a lot easier if you know what they look like. And you'll see even on the next page, we're going to be using these, some of these, when we start with the transformations. So here's graphing transformations now as the next one. Now, what we're going to do is we're going to start and put them in the order that transformations are done. So our first one is going to be this plus minus b. And now notice that all the transformations, like we have an x right here. So x is here, and this side is the y. The writing here g of x means that it is a function of x. Okay, so let's go back to that plus minus b because that is the first thing that we're going to look at. If it is a plus, we are going to the left b times. And now again, remember, we are going to the left. If it is a minus, we're going to the right b times. Now, what this means is, for example, if we have y equals x plus 2, this means that because it's a plus, we're going to the left 2 units. Okay, our next thing that we're going to look at is this a right here. So that is our vertical stretch or shrink. If it is larger than 1, then we vertically stretch by whatever the number is. If it is smaller than 1, we vertically shrink. Next, we're going to look at the pluses and minuses. So if we have a negative outside, we reflect it over x-axis. If we have a negative, why did it not change? Oh, come on. Negative inside, notice that it's here, whereas in the previous one was out here. So if we have that negative inside, we reflect over y-axis. And our last, number 4, is this C right here. If it is a plus, we go up C times, and if it is a minus, we go down C units. Okay, in our next example, we're going to graph the parent function with a dotted line, determine how each parent function changes, and then graph the transformed graph with a solid line. So we're going to be using what we just learned here. Our first one is y equals absolute value of x minus 4. Our parent function is y equals absolute value of x. So we're going to graph our parent function with a dotted line like this. And then we're going to look at, so what are the transformations here? We have a minus 4. When it is inside, like it's inside the absolute value signs, this means that we are going left and right. And now with the negative sign, we are going right 4. So what does that mean? We're going to do 1, 2, 3, and 4 here. So we're going right 4. So we're going to start from here. Uh, 1, 2, 3, and 4. So our graph, absolute value of x minus 4, is going to look something like this. Okay. Our 0 is this where it crosses or it touches the x-axis. So that's going to be our 4 is 0. Our domain, as we can see, it keeps going to infinity and to negative infinity. So it is all real numbers here. Range, it stops at the x-axis and goes up to infinity. So we start from 0, put the 0 in the bracket. Put the 0 inside a bracket and goes all the way to infinity parentheses. And behavior is up to the left and up to the right. Okay. Next one, we have a square root. So our parent function is a square root function, and that one, okay, I pressed something wrong. Sorry. Here, the parent function looks like this. Now, for our transform function, we have a 3 in front of that square root of x. So that means that we are vertically stretching by 3. So it still starts from 0, 0. We're just vertically stretching it. So it's going to go up higher. Our y-intercept now, where does it cross the y-axis or touch the y-axis, is 0, 0. That's where it's on y-axis. Same thing for the 0, which is our x-intercept. That's a 0, 0. Same one. Domain, we start from y-axis and go all the way to infinity. So 0 to infinity. Same thing with the range. We start from the x-axis and go all the way to infinity. Again, it doesn't look like it goes to infinity, towards on the y, but it does keep going. There's no restrictions on it, so it does go to infinity. And behavior is right and up. Okay, next example. And feel free to pause it and try it yourself and see if you get it correct at any point. Okay, this should be y equals. Our parent function is y equals x cubed, which looks something like this right here. Now, when we look at this, we have the negative here first. So we are reflecting over x-axis. And then we have the plus 1. So we are going up 1. So we're going to do this in 2 steps. Our first step is going to be reflecting it over x-axis. So all we're doing is the 0, 0 stays, but we're bringing like this point down here. So it's going to look like this. As if we fold it, or if we fold it along the x-axis, both sides or these curves are going to go on top of each other. So basically bringing, for example, this point as far down here. That's what we're doing with the reflection. Now, our next one is up 1. So we're going to go from 0, 0 to 0, 1. And this is where we're going to graph the actual graph, right, like this. Okay, it's asking for y-intercept. Well, that is where it crosses the y-axis, 0, 1. Domain, we can see that it keeps going up and up and up, and it keeps going down. So our domain is all real numbers, negative infinity to infinity. Why am I getting confused? I am so sorry. That was not the domain. That was the range going up and down. The domain is going left and right. This is the range. This is the domain. So from negative infinity to infinity. Both are all real numbers. In behavior, we are going up to the left and down to the right. And if you see me make any mistakes or hear me make any mistakes on these videos, please let me know. You can just send me an email. Okay, next one. We have an x squared. So our parent function is y equals x squared. Remember, that's the parabola like this, right here. Now, our transformations are, we have this half. So we are vertically, and now since it is less than 1, we are vertically shrinking by a half. So what does that mean? That means that our graph is going to be a lot flatter. Our other thing that we're doing here is this negative sign right here. So we are reflecting across x-axis again. So all of these points are going to come down here on the other side of the x-axis. Okay, our y-intercept here is that 0, 0, the same thing as our 0. Our domain, now that's this side and this side, we are going from negative infinity to infinity. So all real numbers are included. Range starts from the x-axis and goes down to negative infinity. Now, we do need to put the negative side first, so we're going to do negative infinity inside parentheses, and it stops at 0 at x-axis. So again, 0 is included, so it is inside a bracket. Our end behavior is down on the left and down on the right. Okay, let's see. So that was example 2. Now we're going to go on to example 3. We are now actually writing the equation of the function with the following transformations, and then we're graphing it. So our parent function is y equals cube root of x. Translate it 5 units to the right and down 12 units. Okay, so y equals cube root. Now, x is under the cube root. This 5 units to the right is under that cube root as well because it belongs to the x. We're going to the right. Remember, this is the one where we use the other sign. We usually think about going to the right as plus. It's going to be a minus 5. And then we are going down, so we're subtracting 12 from that cube root. So what does that look like? Normally, our parent function would be over here going through 0, 0. But since we're going 5 units to the right, so 2, 4, 6, 8, 10. There's our 5. That's where we're going 5 to the right. And then 12 down. 2, 4, 6, 8, 10, 12. Um, so 5 and 12 are over here. So this is going to be interesting. Something like this. It should be going a little bit farther down on the left side, but that's about what it should look like. Okay, next one is a square root reflected over the x-axis and stretched by a vertical scale factor of 3. Um, so y equals, and we have the square root. Reflected means that there's a negative sign in the front, and stretched by a scale factor of 3 that goes in the front as a 3. Now, our parent function again for the square root looks something like this. We're reflecting it and stretching it vertically, so it'll be something like here. There really should be a larger difference between those two, but it should be 3 times when you're graphing it, but it's without an actual grid, it's hard to graph. Okay, next one, we're going to determine the equation of the parent function. No, determine the equation of the function, sorry. First we do have to determine the parent function. So if we look at this U-shaped graph, we can go to the front, the second page, and see which one reminds it of. Right here, if we look at, well, it looks a lot like the quadratic. So what we're going to do here is we're going to write the parent function is y equals x squared. Okay, is it flipped? No, it is not flipped. So it is not reflected across x-axis. Is it translated left or right? Well, if we think about the quadratic function, it starts from 0, 0. This one is 1, 2, 3 to the left. To the right, sorry. 1, 2, 3 to the left. To the right, 3 to the right. And translate it up or down. Well, yes, it is going 1, 2 up. Is it taller or shorter? No, it is not. And from here, we can write the equation. So it is y equals. Now, this one right here, remember, goes inside. So that goes with the x. And now, since it's right, again, we have the minus sign. Inside parentheses, and this is squared. So the x to the right is with the x inside the squared. And then translating up 2, so it's plus 2. Okay, there we go. Now we're going to go into the application problems. First, we're going to define revenue and profit. So revenue is usually abbreviated as R of X, or the revenue function is R of X. So revenue is price times quantity. Now, profit is revenue minus the cost, right? We take the cost away from what we earn, and that's our profit. Profit is usually marked as P of X, and revenue is R of X, and cost function is C of X. Okay, so let's look at an example. Monthly revenue and costs for the Webster Cell Phone Company are determined by the number of T phones produced and sold as shown in the graph below. So here are cell phones and here are dollars. And notice that cell phones are in thousands, dollars are in millions. And then we have the 2 lines where we have the revenue and we have the cost. Okay, so let's look at our first question. Find the approximate revenue for selling 28,000 phones. So revenue, 28,000 phones. When looking at this, so the difference here is 8. So in the middle here, this difference must be 4. So 8 plus 4 is 12. This is 0, so that has to be 4, 8, 12, 16, 20, 24, 28 has to be over here, right? So we're going to go from 28 all the way up to the revenue function and then go and see how many dollars it is. Well, that's between 2 and 3, so it's got to be 2.5. So it's $2.5 million. Next, we're going to find the approximate cost of manufacturing 28,000 phones. So we're going to take that same 28,000, but now we're going to stop at the cost function and go to the left. And now we end up between 1 and 2, so it has to be 1.5. So 1.5 million. Next, we're going to calculate the approximate profit from manufacturing 28,000 phones. So we're going to take the revenue, 2.5 million, minus the cost, 1.5 million, and we get our profit, which is $1 million. Next, we're going to introduce another new term, which is the break-even point, and that is the point where revenue equals the cost. This same point means because revenue equals the cost, and if our profit is revenue minus cost, then profit is 0. So at the break-even point, profit is 0 and revenue equals the cost. Okay, next question is for what number of phones does the company break even? So we're going to go and find where we have revenue and cost graphs intersect or touch each other. So here's our first one. If we go down, we get 12. And then our other point is over here, and we go down and we see that it's 48,000. So 12,000 and 48,000 phones is where the company breaks even. 12,000 and 48,000 phones. Okay, how many phones should be sold each month if the company is to make profit? So assuming that all phones produced are sold. So we're assuming that every single phone is going to be. If we go and look at the graph here, the revenue is higher up between the break-even points. The cost is lower. So that means that so the area between the revenue and the cost when the revenue is higher is the profit. So that means that it's going to have to be between 12,000 and 48,000 phones as well. If we look at less than 12,000, we can see that the cost function is higher up. So that means that we are paying more than what we're getting from selling. Same thing here if we go higher than 48,000 phones. We're paying more to manufacture them. So we should be, or the company should be making 12,000 to 48,000 phones. Is it more profitable to make 40,000 or 44,000 phones? Explain how you could use a graph to determine without doing any calculation. So let's go and look at this. So 40,000 is right here. If I go to the cost and then I jump up to revenue. So this is the profit. how much money the company gets. Now, 44 is here between 40 and 48,000 right here. So let's see if we go up to the cost and then go up to the revenue. If we look at these two lines that I just drew, the one that is longer is the one with the 40,000 phones. That means that we are making more profit because the gap between the cost and the revenue is larger than with $44,000. So it would be more profitable to make 40,000 phones. Okay. Next, we're going to look at graphing linear functions using intercepts. So our x-intercept, or actually, let's look at function one. Function one, x-intercept. So where does it cross the x-axis? It's right here. That is the point -3, 0. Let's look at function two, x-intercept. Right here is the point 4, 0. So now if we look at both of these points, we can see that our y is 0 in both of them. So in general, our x-intercept is x0. So y is always 0 when we're looking at the x-intercept. Okay, well, what about the y-intercept here? So for function 1, the y-intercept is 0, 2, right here. For function 2, the y-intercept is 0, 3. Again, the common thing for both is that the x is 0 now, and y is where it intersects the y-axis. So for y-intercept, x equals 0. So in this next one, we're going to use the x-intercept and y-intercept to graph each function. So what we're going to do is we're going to find the x-intercept first. That means that we're going to set y2 equals 0 here for this one. So 3x plus 4 times 0 equals 12. And now we're going to solve for x. So 3x plus 0 equals 12. 3x equals 12. We need to divide by 3 to isolate the x, or solve the x. X equals 4. So our x-intercept is 4, 0. 1, 2, 3, 4, right here. Next, we're going to find our y-intercept. So we're going to set x2 equals 0 and solve for y. So 3 times 0 plus 4y equals 12. 0 plus 4y equals 12. 4y equals 12. We divide by 4. Y equals 3. So we get 0, 3. So 1, 2, 3. There we go. And then so graphing, we connect the points here like this. Okay, we've got one more example. So we're going to do the exact same thing. Again, feel free to pause the video and try it on your own. We're going to start with x-intercept. So setting y2 equals 0. 3x minus 0 equals 6. 3x equals 6. Dividing by 3. X equals 2. So our x-intercept is 2, 0 right here. And our y-intercept, we're going to set x2 equals 0. So 3 times 0 minus y equals 6. Negative y equals 6. What we do is we divide by negative 1 to cancel, and we get negative 6. So 0, negative 6 is our y-intercept. So negative 1, negative 2, negative 3, negative 4, negative 5, and negative 6. So there's our y-intercept. And then we draw a straight line right here. Okay, that's it for this lesson 2.1. Let me know if you have any questions. Bye.